Yeah.
Is the wave vectors having one constant magnitude in one particular direction for one particle, or starting from the particle is it having magnitude increase in one particular direction?
So, the wave vector is primarily an indication of the, you can say, the momentum and finally also the energy. Okay, the energy is related to the wave vector. So, we will see that in the case of simple particles, you have a very simple relationship, right. So, h bar into k square, h bar square k square is what we have. Okay. So, with energy and wave vector. So, therefore, if you are looking at wave vector itself, how do you interpret it? Okay. So, we will when we look at the real solids, okay, then we will understand this more. We will use this concept of wave vector to define several other quantities such as density of states, so on, and then we will use that in statistical thermodynamics. But your question is whether it has a yes, it has a magnitude, it is also directional.
It is directional, but what I am asking is, suppose if we consider one particle, and is the wave vector having one single magnitude in one particular direction?
I think if you go back to our single particle system here, okay. So, we were looking at right here. So, in this case you have just one single wave vector in along x, okay, and your E is related to your wave vector, and your wave vector, what it says here is it is quantized because your n is now becoming discrete. Whereas, if you take a particle which is completely free, which is not confined, completely a free particle, freestanding particle, you have continuous wave vectors. Okay. So, whereas now when you put a confinement, you see this wave vector along the x direction is quantized, it is no more continuous in this direction, and it is quantized such that it takes discrete values multiples of pi by d, okay, and correspondingly the energy is related to the wave vector. So, always finally, what is the purpose of this wave vector is to finally calculate the energy. Okay. So, we are relating the energy and wave vector, and then we are now finding how the wave vector behaves in a quantized system. Okay. Now, if you go to a two dimensional case, the wave vector is quantized in both directions, both x and y. Okay. So, this is what we are getting here, and finally, when you substitute this k square, kx square plus ky square into h bar square by 2m. Okay. So, for kx and ky you substitute as pi into L by d, and similarly ky is now pi into n by d. So, that means the wave vector is now quantized in both the x and y directions because of this confinement in both directions. So, what it means physically is that now the energy levels are also becoming discrete. So, when you have continuous waves, you have continuous values of wave vector, the energy values are also continuous. Now, because of the quantum confinement, the wave vectors become discrete and also the corresponding energy values. Okay. Whereas, if you do not confine it in the z direction, still there it will be continuous. Okay. So, and then in the quantum mechanics we describe the wave function. Why we describe wave function is from this we get the probability of deriving other quantities. Okay. The expected values of position, momentum, energy, all this comes from this wave function. Okay. So, correspondingly we have to know the wave function in order to solve the other quantities, but primarily the energy is directly obtained here from the wave vector. Is it clear? So, now as we proceed you will understand more and more what is the function of this wave vector. So, but right now you should understand that wave vector is basically deciding the energy, okay, and if you are confining it, it becomes discrete, if you do not confine it, it is continuous. So, so far so last class we did all this, then we started looking at the quantum vibrational energies. So, we looked at translational energy, that is particle in a quantum well and then particle in a box. So, they are all infinite wells, okay. That is, once the particle is trapped, it cannot come out. So, you can also have finite wells with a finite potential height, potential energy constraint. Okay. So, in that case what happens is, up to certain energy levels the particle is confined, beyond that it becomes continuous. Once it comes out, once the particle can escape this potential energy constraint, then it becomes continuous. So, within the potential energy constraint it becomes quantized. Okay. So, I will give some 1 or 2 problems related to this kind of finite quantum wells in the assignment, you should be able to do it. Okay. So, now the other mode is the vibrational mode. Okay. In the case of classical vibrational energies, we have already taken the example of a spring mass system and we have derived this vibrational energy is the sum of kinetic plus potential energy. So, in the case of quantum microscopic model, so how do we account for the vibrational energy? So, once again, so as I said, you have a very complex representation of the forces of attraction between 2 atoms. Okay. If you consider 2 atoms and the force between them to be approximated by a spring with a spring constant k. So, you can talk about forces of repulsion when they come close to each other, and when they are separated there is an attractive force. So, this is actually your Lennard-Jones potential, okay, which includes both the repulsive and attractive forces. Now, this is more difficult to directly plug in this kind of potential into the Schrodinger's wave equation and solve. Okay. So, therefore, we are going to use a approximation. Okay. So, we use what is called as a simple harmonic model. Okay. A simple harmonic model assumes a parabolic kind of a potential about a mean or about a equilibrium location. So, let this equilibrium location be x naught. So, about this equilibrium location you have a parabolic potential which says that if your distance is more than this equilibrium value, now there is going to be an attractive force, if it is less there is going to be a repulsive force, and that is it. It is a very simple approximation which is fairly accurate. So, now this is your potential energy constraint that has to be plugged into your Schrodinger's wave equation. Okay. So, therefore, in this case the Schrodinger's equation will be minus, so we are going to write this only in the spatial derivative now. Okay. So, we have d square psi by dx square. Okay. We have now the motion of these atoms in the x direction. Okay. They can either come close or they can go far. So, we are describing the corresponding motion by means of waves, okay, by writing the Schrodinger's equation. Plus, now in the original equation we have potential energy constraint minus E times psi. So, now we are going to substitute for this potential energy constraint as half k x square minus E times psi equal to 0. So, this is your ODE in space. Okay. We are now interested mostly in these cases the ODE in space, because this is the one which will give you the eigen value which in turn gives your energy, whereas the one in time it is a standard behavior. Okay. So, we are not too much concerned about bringing the time behavior now, we are mostly concerned about finding the relationship between energy and the wave vector. Okay. So, in this case k is not wave vector, you please do not confuse, this is spring constant. Okay. So, now to solve this again we need two conditions. So, what do we do? Now, this potential energy constraint says that whatever particle is basically trapped within this potential well described by this parabolic potential. Okay. So, very far away from this. So, x going to minus infinity or plus infinity, this particle cannot exist there, because these particles are essentially governed by this potential, constrained by this particular parabolic potential. So, we will impose the condition that psi at either x tending to minus infinity or tending to infinity, the wave function cease to exist. Okay. So, now we can solve this particular ODE, but if you look at the structure now compared to the particle in a quantum well. So, there we did not have any potential energy within the quantum well, we had this directly, we were expressing this in terms of sine and cosine, that was the eigen function, that is the wave function. But now we have k x square, now this becomes a function of x. Okay. So, we have non-constant coefficients. So, we have an ODE with non-constant coefficients. So, we cannot find a very simple analytical functions in terms of trigonometric functions. So, therefore, we can use some numerical methods to solve this ODE, okay, which is giving straightforward results. So, originally this was attempted to be solved using series expansion by Landau and Lifshitz in 1977. Okay. So, this is not so old. So, they were the first to attempt this through series expansion technique, and I will directly give you what is the corresponding eigen value that they obtained. They get E subscript n, because now it becomes quantized. We can write this in function of this number, which can be 0, 1, 2 or whatever. So, we have h nu times n plus half, where your frequency nu is 1 by 2 pi square root of k by m. So, this is the solution after applying the series expansion and solving, let us say this equation 1. Okay. Kind of this looks a little bit familiar, but not so much. So, if you put for example, if you do not have this n plus half, so E is equal to h nu is a common expression that is used to relate for a wave frequency with the energy. Okay. Now, for the vibrational quantized vibrational energies, we have this factor n plus half coming into picture, and n now can take the values from 0 1 till infinity. So, a particle which is basically trapped into this kind of a potential energy constraint given by this parabolic potential will have energies quantized like this. Okay. So, you can imagine this particular potential like this, and you can have multiple modes, multiple wave functions. So, each can take different values of n, so n equal to 0, 1, 2 and so on. So, essentially this potential energy constraint is quantizing this energies to these discrete values. And what is the physical significance? If you put n equal to 0, you have the first energy the corresponding energy for this wave function will be half of h nu, right. Similarly, then this becomes, you have 3 by 2 h nu and so on, right. So, what does this half h nu here mean at n equal to 0? So, this is the ground state. Okay. At the ground state, you still have some value of vibrational energy. That means, even if you do not basically disturb this spring mass system, the quantum mechanics predicts that still this will have some kind of an vibrational energy given by half h nu. Okay. And this has to be some finite value, because again it has to satisfy the Heisenberg's uncertainty principle. So, according to the uncertainty, even at your ground state, some quantum of energy is still there present to satisfy the Heisenberg's uncertainty principle. Okay. So, this is basically what we have to understand about the vibrational energy in quantum mechanics. So, I am not going through all the detailed derivation here, but if somebody is interested how this ODE is actually solved, you can refer to some textbooks related to quantum mechanics and they will be able to provide all the details. Okay. So, let us move on to the other kind of potentials. So, we have covered vibrational energy, we have covered translation energy, what else is left? Rotational energy. Okay. So, we can now look at what quantum mechanics tells us about applying potential energy constraint with rotation. Okay. So, now let us look at a case where we again consider two atoms like this, but now instead of vibrating they are rotating, because for a monoatomic system there is no rotational energy. You should have consider at least a diatomic molecule. So, if you take two atoms, so let us represent this in x, y, z. So, let us say that you have one atom here, you have another atom. Okay, let us consider this as a rigid body rotation. So, we are linking these two atoms like they are rigid, there is no relative motion while rotating. Okay. So, this entire body will be a rigid body which is consisting of two atoms here and they will be rotating. Now, when they rotate in a spherical coordinate system. Okay. That means they can make an angle of theta with the vertical axis. Okay. So, they can rotate like this, and they can also rotate in the xz plane about the y axis. About the y axis also they can rotate. So, that is the azimuthal angle. So, there you can imagine that the projection of this particular object in the xz plane is now making an angle phi. So, this phi can go all the way from 0 to 360 degrees. So, then this will make a sphere. Okay. So, theta going from 0 to 180 and phi going from 0 to 360 will make the rotation completely in a spherical coordinate system. Okay. So, let the mass of one atom be m1, the other one is m2. In a diatomic molecule you do not have to have same equal masses for the two atoms. So, accordingly the moment of inertia will change. If they are equal masses, then you have perfect balance, but here now you can, the moment of inertia can shift depending on the higher mass. So, the distance of this from the origin, let us say it is r1, and from the second atom to the origin, let it be r2. So, this is basically the system under consideration, and the corresponding moment of inertia for this rigid body system will be m subscript r into r naught square, where mr is called the reduced mass, because now you have two masses m1 and m2. We have to write a equivalent reduced mass which is kind of a harmonic mean between the two masses, so m1 plus m2. Okay. So, that means how do you write harmonic mean? 1 by mr is equal to 1 by m1 plus 1 by m2, this is your harmonic mean, right. So, it will always harmonic mean will be biased towards the smaller value, the lesser mass, okay. And the corresponding moment of inertia is this, where what is r naught? r1 plus r2. Okay. So, this is the moment of inertia. Now, why do we have this moment of inertia? So, now let us expand the Schrodinger's wave equation. Now, Schrodinger's wave equation in a generic coordinate system will be what? Laplacian psi is equal to E psi. Okay. So, we will not put any potential energy constraint on this, it is just rotating, just like we have a free electron which is translating. Okay. This can just simply rotate in space without any potential energy constraint. So, that means u is equal to 0. So, now if you expand this in a spherical coordinate system, so the Laplacian now has to be written in a spherical coordinate system. So, your del square will be 1 by r square d by dr, r square d by dr, okay, plus you have 1 by r square sin theta d by d theta into sin theta d by d theta, plus you have variation with respect to the azimuthal angle phi. So, that should be d square by d phi square, and you have 1 by r square sin square times theta. So, here I am going to use, instead of m, the reduced mass mr, because we are considering an equivalent particle with a mass reduced mass mr. Okay. So, this is my equation, and I expand the del square. Now, if you look at the variation with respect to r, so we are only looking at variation with respect to theta and phi, rotation to describe a sphere. So, therefore, there is no variation with respect to r. So, this term can be cancelled. So, essentially we have variation with respect to theta and phi. So, if you write this, you have sin 1 by sin theta. So, I am going to multiply throughout by r square. In fact, here so I will multiply throughout by r square. So, I have d by d theta sin theta into d psi by d theta plus 1 by sin square theta d square by d phi square. So, on this side, so then I am going to so multiply throughout by r square. So, you should have, we can write minus 2 into E I by h bar square into psi. Okay. So, I am dividing throughout by h bar square and multiplying throughout by 2 times mr into r square. Okay, and mr into r naught square I am writing as moment of inertia I. Okay. So, if you want you can just do that step. I skipped a step here. So, basically in this equation if I multiply by 2 times m r, so this becomes del square psi minus E times E by h prime square into 2 times m r psi, and then I am also going to multiply throughout by r naught square. So, I have m r into r naught square here. So, this I am writing as my I. Okay. And in the expansion of Laplacian I have 1 by r naught square, that gets cancelled. So, here r can be written in terms of r naught. Okay. So, you can replace r with r naught anyway. So, that is not going to vary with r. So, you can replace r with r naught. So, this is your Schrodinger's equation with respect to variation in theta and phi. We have again a partial differential equation in 2 dimensions. So, we have to again use separation of variables to separate the derivative of theta and phi, write 2 independent ODEs and try to solve them. So, now we will therefore assume psi of theta comma phi to be something like p of theta and psi of phi. You can use whatever variable you want, but this is what I am using here. So, with this convention, now I suggest you to plug into this PDE. So, let us call this as 1, try to separate it into 2 ODEs. So, if you substitute this, you can write this as psi of phi 1 by sin theta d by d theta sin theta into dp by d theta, because psi is constant now, differentiating with respect to theta. So, plus you have 1 by sin square theta p of theta, you have d square psi by d phi square, because psi is now function of only phi. On the other side you have minus 2 ei psi by square. So, let us divide throughout by psi. So, this psi here, what I have written here is a function of theta and phi. Okay. So, we can divide throughout by psi function of theta and phi. So, therefore, you will have 1 by p sin theta d by d theta sin theta dp by d theta plus 1 by psi, which is a function of phi sin square theta, and we have d square psi by d phi square. So, this is equal to minus 2 e I by bar square. This is, everybody got this? So, just like we have the 2D quantum well. Okay. So, we have a derivative with respect to x, y, and you have the eigen values on the other side. So, this is a constant, the moment of inertia is constant for the system, E is a constant. So, therefore, so you have to have a, so this is a function of theta, this is a function of phi. So, this should be equal to a constant, that means independently they have to be constants. Huh? Yeah, but we will assume in this case, now in the simplest solution that you can get is if you have this entire term constant, this entire term a constant, then you will have another constant. Okay. So, what we will do is, now just like we did the 2D quantum well, we will break this into two further eigenvalue problems. So, one which is 1 by p sin theta d by d theta sin theta dp by d theta, which is equal to some eigenvalue which is k theta square minus k theta square. There in the 2D quantum well we used something like minus L square or minus n square. Okay. So, that means this has to be again a negative quantity here. Okay. So, this side, so if you look at it, so you have a positive value of eigen function E. So, this 2 has to be summed up, then your negative sign will cancel off and you will have a positive value. So, therefore, this has to be a negative value here. Similarly, if you look at 1 by psi of phi sin square theta d square psi by d phi square, we will assume this is some other constant minus m square. So, therefore, essence this means minus k theta square minus m square is equal to minus 2 e I by square. So, we will have positive values of E from this, right. So, therefore, if you write the second, so let us call this as 3 and this as 4, right. So, we have to solve now d square psi by d phi square is equal to minus m square sin square theta psi. Okay. So, this let us call this as equation 5. So, this is the ODE that we have to solve, and from this, once we get these eigenvalues m, we can actually find the solution for 3 also, because we can write this k theta square as basically minus uh, 2 ei plus 2 okay minus m square. Okay. So, therefore, we can directly substitute for, let me put this view, okay. Okay. So, we can directly put this k theta square into equation 3 in terms of m. So, we can write equation 3 in terms of m. So, once we solve the equation 5 and get the m square values, we can actually find the solution to the other ODE as well. You have d by d theta of sin theta dp by plus, now I am writing my k theta square as 2 e I by h bar square minus m square times p equal to 0. Okay. So, I am just substituting, let us say 6 into 3, so that I can rewrite my 3 in terms of m. Okay. So, therefore, let me call this as 7. So, therefore, we can solve first equation 5, obtain m, the eigenvalues m, and then put this into equation 7, put this into equation 7, and then what? Solve for what? E, the actual energy E. Okay. So, again the way you solve it is not as straightforward as the one that you did it in Cartesian system. Okay. You can do this by series expansion or numerically. So, I will only give the final solution for E. Okay. So, the energy eigenvalues. So, we have multiple eigenvalues here. We have m, which is not an energy eigenvalue, but the actual energy eigenvalue is E. Okay. So, the energy eigenvalue solution will be h bar square by 2 times I is the moment of inertia that we have defined. So, we have that I here in the equation 7 and multiplied by numbers L into L plus 1. Okay, you hang on to this, I will come back and say what is L. Now, L is a function of m. So, the m that we have, eigenvalues that we obtain here, is actually rewritten in terms of L, and how they are related. So, your L should be greater than or equal to mod of this number m. The other eigenvalue m is related to this L like this, and your L m can take the values 0 plus or minus 1 plus or minus 2 and so on. And the condition for this L, you can say this is a wave number, these are again in terms of wave numbers, you can express them. So, you can say wave number L should be greater than or equal to modulus of m. So, this is the constraint. So, and depending on that you can calculate the energy of this particular wave function. Okay. So, that means if you talk about, let us say m equal to 0. Okay. So, when you solve this equation number 5, okay. So, you will be constraining, now you will be quantizing it. So, you will have discrete values of m. So, it could be starting from 0, 1, 2, 3 and so on. So, if m equal to 0, what happens? L should be greater than or equal to mod m. Okay, we will see that. Now, if m equal to 0, so what are the values of L that can take? Greater than or equal to. So, it can take 0 and then it can also take 1, 2 and so on. In fact, the way it is written is slightly different. So, let me clarify that. The way it is written, let me, so we can just rewrite it as mod m less than or equal to L, okay, and L can take the value 0, 1, 2. Okay. So, in this case, therefore, if your L equal to 0, so the m has to be 0, okay, and if L equal to 1, so m should be less than or equal to L. So, it can be plus or minus 1, right, or 0. Understand? So, if L equal to 2, so m can be plus or minus 2, plus or minus 1, 0. So, this is the way it is written. Okay. So, you have to start from the lower energy levels and then go to higher energy levels. So, if you do write it the other way, L is greater than or equal to m. So, for m equal to 0, L can go all the way up to infinity, you know. So, usually we start with the lowest energy level and then build upon that. So, the way it is written is mod m less than or equal to L. So, for L equal to 0, we have m equal to 0, that is the lowest energy level, and then for L equal to 1, m should be equal to plus or minus 1 or 0, and then L equal to. So, this is the way you basically fill the energy levels, okay, in the rotational system, right. So, depending on the value of L, so you have two numbers here, one is L, the other is m, okay. And now again we have this concept of degeneracy here. So, what it means is that if you look at say m equal to 0, so L can be 0. So, you have basically in this case two energy levels, you can having the same value of energy, or two wave functions, one for m equal to 0, one for L equal to 0, but the energy is dependent only on L. Okay. So, there is a degeneracy coming again when you go to m equal to plus or minus 1, 0. So, for L equal to 1, you have only one value of energy, but m can be plus 1, minus 1 or 0. So, again you have degeneracy there. You understand? You can have three different wave functions, one for plus 1, minus 1, 0, but all of them having the same value of energy for the rotational system. Similarly, if you go to L equal to 2, what is the degeneracy there? 5. So, in general, the degeneracy as a function of L will be what? 2L plus 1. So, for L equal to 0, the degeneracy is 1, L equal to 1, degeneracy is 3, L equal to 2, the degeneracy is 5. That means, for each of these numbers 0, 1, 2, you have different values of degenerate energy states. That means, they are different wave functions governed by these numbers, but they have the same value of energy, because energy is only a function of L and not m here. Okay. So, this is another good example of degeneracy. The other one that we saw in a two dimensional quantum well. Okay. So, there again the energy is L square plus n square. Okay. So, for values of L equal to 1, n equal to 2 and n equal to 2, L equal to 1, you can have the same energy. Here you have a different way. So, here your energy is function of only one wave number or quantum number. Okay. That quantum number is only L, but actually the ODE is governed by two quantum numbers, L and m. Okay. But it does not, the energy does not recognize that. So, that is why again there is a degeneracy in this problem. You have although different wave functions, you have the same value of energy. So, same energy level is being occupied by multiple wave functions. So, this is another example, good example of degeneracy in the rotational system. You understand?
So is it the same like that electron has that the rotational momentum quantum arc and that magnetic quantum number? What quantum number?
No, yeah, it is somewhat similar to that, but this is only rotational system that we are considering. In rotational system, you have a quantum number with respect to theta direction, we have one quantum number with respect to phi direction, but the energy is function of only one quantum number. Okay. So this kind of concept of degeneracy is only typical to the quantum mechanical systems. Okay. So, let us quickly do the last part of the quantum mechanics, which is these are the fundamental quantum mechanics that we are talking about. So, these are for what we call as electronic energy levels. Okay. So, whatever we have done, they are also for mechanical energies, talking about translation, rotation and vibration. You can talk about filling of electrons, that is what you are asking about, the orbital concept. So, they start with the lowest orbit, go to the highest. So, what is basically causing this to do? So, basically filling of electrons from the lowest energy level to the highest energy level, and that is also predicted by quantum mechanics. So, we will therefore look at this very briefly. This is not very important for heat transfer, but just to also complete it. So, electronic energy levels. So, here we take a very simple example of a hydrogen atom. Okay. So, you have how many electrons are there in a hydrogen atom? 1. Okay. So, you have the nucleus, and this is a simple model where you have an electron orbiting the nucleus. So, we are going to expand this model, simplistic model, to other atoms also. We will assume even other atoms, we can predict it by assuming the electrons keep rotating around this particular nucleus as the center, and therefore, we have to consider the force of attraction between the nucleus and the electron as the potential energy constraint in the case of electronic energy levels. So, this is given by your Coulomb's potential. Okay. So, this is your standard potential. The Coulomb's force says that if you have an electron separated from the nucleus at a radius r, so the force is 1 by 4 pi times the permittivity of free space into the charge of the electron square divided by r square. Okay. So, therefore, the potential energy can be determined as F is equal to du by dr. So, we can integrate F as a function of r. So, therefore, u of r will be what? Minus E square by 4 pi epsilon naught into r. So, this becomes your potential energy constraint. Okay. So, you can substitute this into the Schrodinger's equation again as the new potential energy constraint. Now, this is again a spherical system, this electron orbiting the nucleus. So, therefore, however, we are not interested in variation with theta and phi now, only with the radial direction. So, we are interested in the energy quantization only in the radial direction. Therefore, whereas in the rotational energies we discarded the derivative of r, now in the case of electronic energy we will discard the other two directions. So, these two can be neglected and we will have only the derivative with respect to r. Okay. And you can substitute the Coulomb's potential energy as the potential energy constraint, and if you solve this once again by the separation of variables, which is not as straightforward. So, we will get an expression for the eigenvalues of the electron filling. So, which is minus capital M. So, the M now becomes the mass of the electron in the Schrodinger's equation, okay, that I am writing as M here, C1 square by 2 h bar square n square. Now, this C1 is this constant, basically E square, I think it should be E square by 4 pi epsilon naught. Okay. So, for the case of electron, if you substitute the mass of electron, then find out this constant, and therefore, your modified Planck's constant, then this becomes minus 13.6 electron volts divided by n square. Okay. And what is n? So, n is greater than or equal to 1, and we have other quantum numbers coming into picture, which is not in the energy, but while you solve the equation you will have quantum numbers. So, that is L plus 1 and modulus of M should be less than or equal to L, and your L can be 0, 1, 1, 2 and so on. Okay. So, the energy is a function of only n, but n is dependent on the quantum number L, okay, and again you have another quantum number M, for which it can take the values depending on L is equal to 0, 1, 2 and so on. So, you have multiple quantum numbers, but finally the energy is a function of only one quantum number n. Okay. So, again you have a degeneracy here, right. So, therefore, now depending on the value of n, you can start filling the electrons in an atom. Okay. So, for n equal to 1, so this is the first electron occupying the our first orbital. So, the corresponding energy of this electron is minus 13.6 electron volts.
So, if
and as you keep increasing your n, so this value keeps reducing.
if the wave function is just the function of r, how can there be more than one quantum number?
Yeah, that's a good question. I think when you are solving the so I think we should also use the, you are right. So, it should also be a function of theta and phi, you are right, because we also consider the rotation of this electron around the nucleus. So, finally, you are right. So, I think we cannot neglect the theta and phi dependence. So, when we do the separation of variables, I think we should have psi should be something like some r, which is a function of r, and we will have another y, which is a function of theta and phi. Now, this will have the quantum numbers L and M, and this r will have the quantum number n. You are absolutely right. So, that the wave function now becomes function of both of all the three wave quantum numbers n, L and M. You are right. So, in the case of rotation system, you have only two wave numbers, okay, two quantum numbers. So, in the case of electronic energy, you have to consider all, it is a 3-dimensional system now. So, we cannot therefore neglect the variation with respect to theta and phi. Okay. So, the separation of variables, therefore, we will have quantum numbers appearing for theta and phi, which are L and M, and for r you have quantum number n. So, that is why now you have a additional level of degeneracy coming in. Okay. So, we will stop here. I think tomorrow I will just talk a little bit about this filling of the electrons and how these orbitals have come. So, very briefly, and then we will slowly conclude the quantum mechanics, then go to the next topic. Okay.